So sorry for the delay. So my name is Justin Molloy, and I'm from the newly formed Francis Crick Institute in London, which is about to open this October. So this will be the largest biomedical research institute in the UK, one of the largest in the world actually. And I used to be in what's called the National Institute for Medical Research, which is funded by the Medical Research Council. So actually they funded a lot of the work I'm going to tell you about. So I know you've already had one lecture from Professor Lamelis, I think earlier last week on optical tweezers. So this is sort of a follow-on from that, and I'm going to focus mainly on the use of optical tweezers for studying the mechanical properties of single molecules. So this is making high-resolution mechanical measurements in the sort of piconewton nanometer range using laser light. So the plan of the lecture. So the lecture plan is as follows. What I'm hoping to tell you about is how optical tweezers happen to have exactly the right mechanical properties to push and pull on single biological macromolecules, because they exert forces of a few piconewtons, and because of the way that they're coupled into a light microscope, you can get positional resolution in the nanometer length scale. So that's about the size of a biological molecule. Typical biological molecules, proteins, are of the order of a nanometer or so across. The time resolution of the measurements is limited by the mechanical response time of the optical tweezers, and that takes you out into, well, most of the published records are in the range of about 10 kilohertz, but actually this has recently been improved up to about 100 kilohertz, and that takes you into the regime where you can look at protein conformational changes, so we can get down to sort of microsecond time scale. It's possible to measure mechanical events which are powered by the energy of a single ATP molecule. So the energy provided by one molecule of what biologists would call the fuel, which is adenosine triphosphate, that amount of energy is only about 10 times thermal energy, but you can distinguish between the background thermal noise and the energy that's provided by the ATP molecule using this technique. And a lot of that has to do with the fact that it is this very soft mechanical system. Optical tweezers, because they're coupled into a light microscope, which is sort of the workhorse of biologists, it's compatible with many other optical laser-based methods. And one of the things is to combine 2 or 3 different methods simultaneously as you make measurements, so that you can sort of cross-correlate a measurement, let's say, of fluorescence with the mechanical response. And if you have 2 signals and you can put them together, then you get even more information. So it's ideally suited for those sort of cross-correlation methods. And then finally, what I'm going to spend most of my time talking about are the properties of what we call motor proteins, which are proteins that take the energy of ATP and convert it into mechanical force of movement. And they become a model system actually not only for the development of optical tweezers, but also for a whole variety of biophysical methods. And very often these protein systems are the kind of what you would call the go-to bit of biology, because of the fact that they're very well understood biochemically, and because they have these very interesting properties of converting chemical energy into mechanical work, and so that they're just great for studying for physicists, biologists, and engineers. So I'd sort of make the case that they're sort of a paradigm, a model system for looking at biophysical biophysics of molecules. Okay, so now on with the lecture. So let's first of all think about optical tweezers, and you've probably heard about this before. It's rather early in the morning, but let's just all do a quick calculation. So I never, as a biologist, I never thought I'd be privileged enough to write E equals mc squared in one of my lectures, but actually this is where it all comes from. Because just taking this, Einstein's equation here, we know that if this is the energy, this mass, the speed of light squared, the momentum of a photon, which is the mass times the velocity, by just rearranging this equation, is the energy over the speed of light. And so that's the energy in a single photon. And if we want to measure the force that a photon will exert when it impacts on something, we need to know what the change in momentum of the particle is. So the change in momentum, and so the momentum is mc divided by time. force, and that is just introduces to P over C, where P is the power of the light beam. So, let's do our simple calculation. So this is about a 1 milliwatt laser here. Okay, so I'm now going to shine this at this screen, and I'm going to shine it actually on a black thing first of all, so it's all absorbed. So, well, there's a little bit of light coming back at us, but let's pretend that the entire milliwatt of light is bouncing into there. All the energy from the light all the momentum of the light goes into this projector screen. So it's 1 milliwatt, so 1 times 10 to the minus 3, divided by the speed of light, which is
10 to the
8. Okay, so we do that very quickly. So it's 10 times 10 to the 8. It's about 0.3 times 10 to the minus 12. Is that right?
Yeah.
Okay. And 10 to the minus 12. What's that in sort of engineering language? We've got sort of micro, nano, pico. Okay, so 0.3 piconewtons. Okay. And actually, interestingly enough, it's 0.3 piconewtons if I shine it on something black, but if I shine it on something which reflects, then it goes up to 0.6 piconewtons. That's because the energy of the light's actually you get double, because it's come back out again. So it's, anyway, so just with a simple laser pointer, we can produce a force of the order of a piconewton. So how do we harness that force? I mean, it's not a lot of force, but actually a piconewton is just right for what we want to have to manipulate proteins. But how do we harness it? And this, all of the early work was really done by this guy Art Ashkin in the Bell Labs, and he came up initially with a configuration back in 1971, 2 different laser-like configurations which would produce an optical trap or an optical potential well, where the force exerted by light was such that it would direct things towards the centre of the beam. So if you have a Gaussian laser beam, so most of these lasers are brighter in the middle than at the edge, because they're sort of diffraction limited, and you focus that beam down to a small spot, maybe of the order of 1 or 2 microns, then the momentum that the light imparts to that particle, because it's bouncing onto the back of this particle, tends to push the particle forward, and actually then these things become trapped because they're just pushed against this solid surface here. So if you observe from this side, you'll see particles enter the beam and then get pushed onto this face over here, and eventually particles just pile up as a little mound of particles. So it's not really a trap, it's just a way of just gathering things into a little spot. So he then came up with a second configuration, which is to say, okay, rather than having a solid interface here, let's just have 2 counter-propagating laser beams. So by carefully aligning 2 lasers so they pointed exactly at each other, we've now got the momentum of this beam tending to push particles in this direction, and ditto the other one. And because the beams are focused, you'll end up with a sort of null point in the middle here where the force is exactly balanced. And now particles will enter this beam, travel down this way, and then travel down this way and come to the focus, and same with this particles. So now again we get a sort of pile-up where things now are held in 3-dimensional space in the middle of the volume. Okay, so this, and in fact this technique is still used in some labs. So one of the great people in this field, Carlos Bustamante, in fact still uses this counter-propagating geometry for doing many of his experiments. And the advantage of it is that you can produce very high trapping forces. In fact, you can produce forces up to close to 100 piconewtons using this technique. But actually a more elegant method, which again Ashkin came up with, it was 15 years later, 1986, was this thing called the single beam gradient trap. And this is what most people use when they do optical tweezers or optical trapping, because of its simplicity really, that you just now have a single laser beam, and if you use a microscope objective lens, so that you can focus the beam to a diffraction limited spot now, so it now comes down to a spot size of about 1 micrometer, and you have incident rays which enter the particle at angles of up to like 100 degrees, so very steep incident angles. You now produce a vector in the force here, which acts upwards and back towards the focus. So now we have a 3-dimensional trap where the particle enters the beam and actually then sits just below the focal spot. And So that's called a single beam gradient trap. And just look at those, the origin of the forces again. Let's just think of a light ray coming through this side of the particle. As it's refracted and then exits on this side, that imparts a reaction force in this direction. So that explains the lateral transverse force. And if the light is more intense on the left than on the right, so if this is the centre of the beam, the particle moves towards the centre of the laser beam. Okay, so you have a Gaussian intensity profile. Less force this side, more force this side, so it moves towards the centre. Now with this gradient, three-dimensional gradient trap, we have a light ray which comes in here, refracted, and again, and the net force is up this way, it's the same on this side, so the particle will sit just below the focal spot of the laser beam. And the beauty of this is now that you don't have to make two beams completely, perfectly coaxial. You just have a single beam, and that means that you can just, by moving that one laser beam, you can move the particle around. So it's very simple now to manipulate things. You just move one laser beam. You don't have to move two laser beams simultaneously. So how do you actually realise that inside a light microscope? And the answer is that you have a laser coming into the side of your optical microscope, and then you simply reflect it off either a half-silvered mirror or a dichroic mirror, so that the laser beam then enters the back aperture of the objective lens, and if it enters parallel here, the objective lens will focus it for you to the diffraction limit spot, and then by moving the laser beam over here, you move the spot and you move the object that you've captured. And in order to do this manipulation, you just need a simple two-lens, what's called a telescope system. And so the important thing here for people who want to build this is that you need two lenses, and they want to be, you want to have your steering mirror one focal length away from this back lens, spacing between these two lenses of 2f, and then the spacing between this lens and the back aperture of f. And when you do that, when you tilt this mirror, you change the angle of the beam here, which translates the spot in this plane, which then changes the angle as it enters the back aperture. So it always goes through, exactly through the back aperture, but you just change the angle, and when you do that, you translate this spot in the XY plane. So the spot stays in plane, and so it's just simply the movement of one mirror here, and you can move the spot in X, Y, and Z. Okay, so as I say, it's very simple to build one of these optical traps. Laser, one mirror, two lenses, and that's it. So you can go away and build that tomorrow if you wanted to. And in fact, when I first started off with this optical tweezers, I went into a laboratory which was doing Raman spectroscopy, and they, for a period of 20 years, have been coupling a laser beam into the microscope to look at Raman spectra from wool samples. And all I had to do, actually, for their system, I just had to put one lens in, put in some plastic beads, and then you see this magical effect of these beads just getting drawn into the spot of light. And it's the first time you do it, you go, whoa, that's amazing, because it is just such a stunning thing to be able to just see a little particle get trapped and then move around. It's very simple. And so Ashkin, as I say, brought this technology into the world of biologists, because the first things he started trapping actually were biological particles. He was trapping viruses and bacteria, for instance, and he teamed up with biologists to do some early experiments, just grabbing hold of E. coli, which is the gut flora bacteria. He could pick these things up and trap them and stop them from swimming. And if he turned the laser off, then they'd swim away, proving that the laser beam didn't actually destroy the bacteria. The bacteria was quite happy and could go and swim away after it had been captured in the optical trap. Okay, so although that's the simple thing, so it took I think half an hour to build my first optical trap, and then it took nearly 3 years to build the proper one. And of course, when you want to do a measurement with such a system, you then have to bring in all sorts of other things in order to manipulate things with high precision, and to measure the position of the particle with very high accuracy, and of course then do all the computing to capture the data and analyze all the data. And so you start off with that, wow, fantastic, this is really easy, and then you just have to grind away building the blasted things, and I'm sure many of you are involved in such things where you're actually developing apparatus or developing techniques, and you might spend a year or many years building a piece of apparatus, and the experiment that you're going to do is probably going to be over in like 1 millisecond.
Yeah.
Okay, so you spent 3 years in order to do a 1 millisecond experiment. But as long as that 1 millisecond is important and is answering important question, it's all worthwhile. So I sort of felt it was in the end, actually, with this sort of Frankenstein machine. So I'm going to talk more about this device, how it works, and the sort of measurements that well, my group and other groups have got out of these optical tweezers over the years. So I'm just going to tell you a little bit. So a little bit more about the mechanical properties. I know some of you are physicists and some aren't, but anyway, hopefully I'll explain this in a way that is not too stupid for the physicists and not too muddling for biologists. So this is the way that physicists or engineers would consider a sort of mechanical system like this. So if you have this sphere here is supposed to represent the particle that you've captured in your optical trap. And the equations of motion of that particle, in other words, what is that particle going to do? What are the forces that are governing the motion of that particle? And really there are three different sources of mechanical input. There's the acceleration, the force, which is mass times acceleration of the particle. So that's energy, and then we have the viscous damping, which is this beta, and that is proportional to velocity. So depending on how fast the thing is moving through the solution, that viscous force will increase. And then finally, you have the displacement. So this is the final force that we're going to add in here, and the displacement is proportional to the extension of this spring. So that's a linear relationship. So we have the sort of second derivative, first derivative, and then just the straight displacement. And that essentially governs three forces which are that are tending to interact with this particle. And at equilibrium, the sum of all three must be equal to 0 because it's not going anywhere on average. So on average, we assume it stays in the same position. So we know the sum of these three components is 0. Let's just consider each one of those in turn. So let's think first of all about the mass times acceleration. Well, there's a simple equation which relates how rapidly this particle will move given it's suspended on a spring, and that's given by this equation here, which is the spring constant, kappa, divided by n. The square root of that, times 1 over 2 pi, gives you what's called the resonance frequency. So if you have a particle on a spring, and you just move the particle and then watch it bounce up and down, the frequency at which that particle will move up and down depends on the stiffness of the spring and the mass of the particle. And in this system, when you put in reasonable values for kappa, the stiffness, and m, the mass is about 10. The mass is about 10 to the minus 16 kilograms. So because the mass is so tiny, and this is a very small number, you'll end up with a very high resonant frequency, about 50 kilohertz. So its natural frequency would be about 50 kilohertz. Let's now think about the damping constant. This is this beta term. Well, the damping comes about because of Stokes drag on the particle. So because you have a spherical object, this 1 micron or so particle, moving through water, the water has to get out of the way, and that takes a little bit of energy, and that produces viscous damping. And that is given by Stokes' law here, 6 pi eta, which is the viscosity of the water, times r, which is the radius of the particle. And if we now want to know what the time constant, if you pull on this spring, what's the time constant of the motion of this particle? And again, is given by this simple equation here, which again involves the spring constant, kappa, and the beta. So the stiffer the spring, the faster it will move. And the smaller the beta, in other words, the less viscous, the faster it will move. So a particle moving in air will move very rapidly. A particle moving in honey, if you pull it, it'll just only move very, very slowly. And so we can work out what this damping time constant is. And the answer is when you, again, plug in reasonable numbers for beta and for kappa, we now land up with a time constant of something like about 1 kilohertz. And so engineers would say this system is over-damped because this drag term is very much slower than the resonant frequency. And because it's overdamped, in fact, we can just ignore this mass term altogether. So for all of the things that I'm talking about, I mean, basically whenever you consider optical tweezers, you usually just remove you just forget the mass. You just consider it as a massless particle. Okay, so that's that. So the time constant here, this 1 kilohertz value. The important thing about that is that tells you what the mechanical response time of the system is. So if you have, sorry, the spring is representing is representing the optical trap, obviously. But if something pulls on the particle within the optical trap, the response time will be about 1 millisecond, something like that. Okay, so now let's look at some data. So if you take a 1 micron particle, hold it in an optical trap, and then you just follow its motion with time, and you look at the position of the particle, you find that it fluctuates about the midpoint here. And the reason it fluctuates is because there's underlying thermal noise. So the particle, of course, is being bombarded by water molecules, which are at room temperature. So the average thermal energy of the particle is it's the sum of all those interacting molecules, but it always reduces down to a half kT per axis. So the particle has this much energy, and then you say how much is it going to move, and there's this principle called the equipartition principle, which says that the energy that you put in has to go somewhere, and the place the energy goes is into the spring constant times multiplied by the square of the distance from the mean rest position. So that's the energy that we stored in the spring-like stiffness of the optical tweezer, and that exactly balances the energy that's put in by thermal energy. And so this equipartition principle tells us that the particle will fluctuate in position around its mean rest position, that's at the center of the optical trap, and the root mean squared deviation, well, in this case, is going to be about 14 nanometers. So if you put in values for Boltzmann's constant and temperature, and you put in values for your kappa, your x squared value comes out about 14 squared. Okay, so now if we look at the scale here, let's just look at what this is actually in nanometers. So go away from this equation and actually look at the numbers. The scale here is in nanometers, and so it's fluctuating in position from the peak to peak value is about 40 plus or minus 40 nanometers. As I say, the RMS, the root mean squared value, is about 14. Now that actually presents a problem immediately for studying mechanical properties of molecules, because this peak-to-peak noise is probably 5 or 10 times bigger than a biological molecule. So you're trying to measure, if you want to measure the conformational change of a molecule, which is, let's say, 5 or 10 nanometers, and the noise in your system is 20 or 40 nanometers, you've actually got more noise than signal. So you can see immediately it's going to actually be quite a tricky measurement to make. So we have this underlying thermal noise becomes quite a contaminating problem with our system. We're actually working below as it were, the thermal noise limit. And I mentioned about that response time of the system. Well, actually, in fact, just looking at this data, you can see that it's not what would be called white noise. These points are correlated with each other in time. If each point was completely uncorrelated, the points would be dotted just randomly all over the place. But we can see here, just by looking at the data, that sorry, I keep pushing off my fingers. We can see here these points are actually, to some extent, correlated in time. The position at this point sort of determines the position of the next two following points. They're not. You would never have a point immediately down here and up here. And that comes across in this what's called power spectral density of the noise. And rather than being white noise, this is the frequency here, and this is the amplitude of the noise. Rather than being white noise, which would be flat across the entire frequency spectrum, this shows this what's called a roll-off, so that high frequency noise is at much lower amplitudes than the low frequency noise, and actually the characteristic, what's called F0 or FC, the characteristic roll-off frequency, in this particular example here is about 200 hertz. And that's because of the trap stiffness. If you increase the trap stiffness, this will move out to higher frequencies. We'll see that in a moment, actually. So let's see that here. So this is what we've done here is to take the optical tweezer and move it back and forth with the square wave, and the particles, when I move the optical tweezer over by, let's say, 400 nanometers, the particle then has to diffuse across into the new rest position. I then move the optical trap, particle sluggishly moves it back again, and so on. And you can look at that, the speed at which it returns in the new trap position is given by this rate constant, and at low powers, 120 milliwatts here, that rate constant is about 500 per second, and at higher powers it goes up to about 2,000 per second. And if you think about it in terms of that power spectral density which I was talking about, this would correspond to a power spectral density of about 80 hertz, and here it's about 300 hertz. So by increasing the laser power, you increase the stiffness of the trap, increase the kappa, and so you increase the response time. So to get the best response time out of the system, you want to work at very high trapping stiffness. Now let's look at it actually in action. So when that's the end of the sort of the method, the sort of engineering stuff. Now we're just going to talk about the biological measurements that we've used, we've made with the optical tweezers. So this is this is sort of a standard research microscope. There's a laser down here, and it goes through this little optical circuit, comes into the back of the microscope, and then up through the objective lens. It's an inverted microscope, so the light path goes upwards and then into the room. And then these are 4 particles. Do that little dance. Okay, so these are 1 micrometer plastic microspheres, and these are diffusing, just showing just normal Brownian motion. And these 4 clearly aren't diffusing because they've been caught in the optical tweezers. And we've got 4 particles, we're trapping 4 particles simultaneously here by time sharing the laser beam. So in fact, on this optical light circuit here, there's a device, an acousto-optic deflector, which can deflect the beam in 2 axes with a time resolution actually of about a microsecond. So you can move the beam very rapidly to a new position. And so by going round to 4 different positions and just rapidly cycling around those 4 positions, you essentially synthesize 4 traps. You can synthesize up to about 16 traps quite routinely by doing this time-sharing method. And then it's just a matter of writing a computer program to send the right signals to the device, and you can then move as many particles you want and put the particles where you want them to be. Okay, so this is just a sort of a demonstration of ability to just manipulate things. So now we've made our device, what are we going to do with it? So we can pick things up and move them around. Let's now think about the biology and what we're going to do with the tweezers. So the biology bit is this. I mean, I worked on sort of single molecule experiments for I guess the last 20 years. So I'm completely I'm a single molecule person. But when you say you want to work on single molecules, people would just say, well, why do that? Why not just take a tube of the stuff and get a nice big signal, measure what you want to measure, and get on with life? But it turns out that just by looking at a single molecule and the response of a single molecule, you can get a different kind of information about how those molecules behave, particularly when the response will be lost if you look at the bulk population. I'm going to come to this idea in a minute, but the other fact is that many biological molecules actually operate as individual single molecules. So if you think of the following sort of senses, for instance hearing, so that the quietest sound that you can hear is activated just by a single channel which is positioned in the inner ear, which is attached onto a little thing called the sensory hair cell. And when a mechanical wave comes in and displaces those that sensory cell, it opens a single channel, and you can hear very close to the thermal limit. Your perception of sound is only about 5 to 10 times thermal energy. That's how good your ears are. And in order to be that good, you have to work close to the single molecule level. And so a lot of physiologists have studied mechanisms of hearing at the single channel, single hair cell level, and for that very reason, because that's that's how it works. You know, that's a bit of biology that works at the single molecule level. Similarly, smell. So your olfactory system, you have about 800 somewhere in your nose. You've got 800 different what are called G protein coupled receptors. These are proteins which will bind a ligand, and then in response to binding the ligand, will produce a downstream signal which eventually gets to your brain somehow and tells you that you smell lemon or orange or some odour. And you do that rather than like your colour vision. If you notice, if you've got just 3 different kinds of receptor in your eye, in your nose, as I say, you have essentially about 800 different proteins which are trying to look at that great panel of different smells that you're able to sense. And that's done by a diversity of these receptor molecules. But each cell type will express a single type of receptor, and so it will be responsive to a single type of ligand. And at the level of actual detection, you can detect close to a single molecule binding to one cell in your nose. And actually, we're interested in these receptor molecules for that very reason. And then finally, vision. Again, your eye is very close to measuring single photons. You can actually measure it's something like 5 to 10 photons. I think that your eye can detect at the absolute limit. But ultimately, it can be a single rhodopsin molecule which is changing state to give you the sensation of light. Anyway, so those are human senses which work very close to the single molecule limit. But in fact, the paradigms for our single molecule studies come from these 2 systems here, nerve and muscle. And the reason is that these 2 biological systems were extensively studied, well, have been extensively studied for like 50 years or more. And our understanding of how nerves conduct electricity and how muscle produces force, our understanding of that moved from a sort of bulk measurement down to the level of trying to understand how the individual proteins work. And the big block in both of these studies were, okay, we know that a nerve can depolarize and emit ions across the membrane, and we believe that happens by a single protein opening and closing. But can we actually see that individual protein, let's say, open and then close again? And can we, with a muscle fiber or with a muscle, can we see an individual muscle molecule produce a very small amount of force and movement in response to a single ATP molecule? Okay, now let's go. Good. So let's now come on to that. So how would you measure the properties of a single molecule? And what do you get out of it at the end of the day? So I mentioned your eyes and photons. Let's think about energies involved in any one of those single molecule detection systems. So when light impinges on your retina, light has an energy of about 400 piconewton nanometers. I'm going to use mechanical work terms here. That's actually 10 to the minus 21 joules. The reason I've got mechanical work terms, you can refer that back to thermal energy, kBT, which I mentioned earlier. That's 4 piconewton nanometers, 4 times 10 to the minus 21 joules. That's the number that you need to remember. That's your noise floor. So one photon has about 100 times thermal energy. One ATP molecule has about 25 times thermal energy, and that's, when I say that's the energy of ATP, that's when ATP, when the terminal phosphate of ATP is cleaved, leaving you with ADP and phosphate, and that's the energy change in piconewton nanometers. And when one ion moves across a cell membrane, so I'm not going to do very well with this now. When one ion moves across a cell membrane, the work done in moving that charge across through that potential difference is 10 piconewton nanometers. So a single ion, a single potassium ion or sodium ion going across a nerve membrane, that's the amount of energy involved. And in fact, no one has yet measured the transit of a single ion